A line of earthquakes has been quietly unfolding far from the crowded streets and busy coastlines of Luzon. Day after day, instruments positioned across the region have detected fresh tremors rising from the floor of the South China Sea, west of Pangasinan and Ilocos. Most residents never felt them. Fishing boats continued their routines, waves rolled toward familiar beaches, and life moved forward with little indication that a restless tectonic boundary had become noticeably more active. Yet every new seismic signal added another point to a growing pattern that geologists cannot simply ignore. During the past several weeks, a succession of earthquakes has occurred along the Manila Trench, including a magnitude 5.0 earthquake, approximately 66 miles, or about 106 kilometers, west-northwest of Cavite, Pangasinan, followed by numerous magnitude 4.9, magnitude 4.7, and smaller earthquakes concentrated within the same offshore region. Many of these earthquakes originated at depths of approximately 6 miles, or 10 kilometers, suggesting that the activity is occurring within the shallow portion of the tectonic system associated with the trench. Reports from Philippine monitoring agencies documented dozens of earthquakes during this period, representing one of the more concentrated episodes of seismicity observed there in recent months. For scientists, earthquakes rarely exist as isolated events. Every rupture becomes another clue in a much larger geological puzzle that has been assembling over millions of years. While no earthquake swarm automatically signals the approach of a catastrophic event, neither can persistent activity along one of Southeast Asia's most dangerous subduction zones be dismissed as meaningless background noise. Modern seismology is built upon careful observation rather than speculation, and observation is exactly what has intensified across the Manila Trench. Stretching for hundreds of miles along the western margin of Luzon before continuing southward toward Mindoro, the Manila Trench marks the collision between two enormous sections of Earth's outer shell. To the west lies part of the Sunda Plate, representing the southeastern extension of the Eurasian Plate. To the east lies the Philippine Mobile Belt, an extraordinarily complex collection of crustal blocks compressed between opposing tectonic forces. Unlike a crack that simply separates two pieces of rock, this boundary is a gigantic conveyor system operating at a pace far too slow for human eyes to detect. Year after year, the oceanic plate gradually descends beneath the Philippine Mobile Belt. The movement amounts to only a few inches each year, roughly comparable to the rate at which human fingernails grow. Yet those few inches accumulate relentlessly across centuries, storing unimaginable quantities of elastic strain inside rocks that appear perfectly motionless from the surface. Such slow motion creates one of geology's greatest paradoxes. The landscape appears stable, mountains stand unmoving, coastlines seem permanent, entire civilizations rise and fall without witnessing major changes. Hidden within the crust, however, enormous forces continue accumulating every single day. The Manila Trench exists because one tectonic plate is forced downward into Earth's mantle through a process known as subduction. As the descending slab sinks, it drags against the overriding plate above it. In some places, the rocks slide smoothly, releasing stress gradually through countless tiny earthquakes. Elsewhere, the rocks become locked together, refusing to move despite the immense pressure attempting to force them apart. Those locked sections are what concern earthquake scientists most. When enough stress eventually overcomes friction, decades, or sometimes centuries, of accumulated strain may be released within only a few minutes. The resulting rupture can produce one of nature's most powerful events, a megathrust earthquake. Megathrust earthquakes differ fundamentally from the shallow crustal earthquakes that many people are more familiar with. Instead of rupturing along relatively short faults inside continental crust, megathrust earthquakes occur where entire tectonic plates collide. The rupture surface can extend for several hundred miles, while vertical movement of the seafloor may lift or lower enormous volumes of seawater almost instantaneously. That sudden displacement creates the conditions necessary for tsunami generation. History has repeatedly demonstrated the destructive capability of these events. The Indian Ocean earthquake during the year 2004 produced devastating tsunami waves across multiple countries. The Tohoku earthquake of the year 2011 transformed portions of northeastern Japan within minutes while generating tsunami waves that crossed the Pacific Ocean. Neither event occurred along the Manila Trench. Yet both serve as reminders of the immense energy stored within active subduction zones around the world. Among Philippine trenches, the Manila Trench has attracted increasing scientific attention because of its geological characteristics and its proximity to densely populated coastlines. Numerical simulations conducted over the past 2 decades consistently indicate that a sufficiently large rupture along portions of this trench could generate tsunami waves capable of reaching western Luzon within only a few minutes, leaving little time for official warnings after the earthquake begins. Numerous peer-reviewed studies have therefore focused not only on earthquake hazards, but also on tsunami propagation across the South China Sea. Understanding why requires looking beyond individual earthquakes. Seismicity often resembles a language spoken by Earth's crust. Most of the time, the vocabulary consists of countless tiny events occurring almost continuously. Occasionally, that language changes. Earthquakes begin clustering in one location. Activity migrates along a fault. Depths shift. Magnitudes increase or decrease. Sometimes these changes represent harmless adjustments within the crust. Other times, they reflect evolving stress conditions. The difficult part is determining which explanation applies. Researchers have spent decades studying earthquake swarms across numerous tectonic environments, including volcanic regions, transform faults, and subduction zones. Their findings reveal that swarms possess many possible causes. Fluids moving through fractured rock may trigger clusters of earthquakes. Slow slip events occurring deep underground can redistribute stresses. Small ruptures may relieve accumulated strain instead of increasing danger. In other situations, swarms precede larger earthquakes, although most do not. That uncertainty remains one of the greatest challenges in earthquake science. Despite extraordinary advances in satellite geodesy, ocean bottom seismology, artificial intelligence, and high-resolution seismic imaging, no scientific method can currently predict exactly when or where a destructive earthquake will occur. This distinction is critically important. An increase in earthquakes along the Manila Trench does not mean a magnitude 8.4 earthquake is about to occur. At the same time, scientists do not ignore unusual activity simply because prediction remains impossible. Instead, every earthquake contributes valuable information regarding stress distribution, fault geometry, rupture behavior, and long-term tectonic evolution. Recent earthquake clusters offshore Pangasinan therefore represent important scientific observations rather than definitive warnings. The Philippine Institute of Volcanology and Seismology has consistently emphasized this balance between awareness and caution. Officials have explained that several active trenches surrounding the country are capable of generating very large earthquakes, while also stressing that no available technology can determine precisely when such events may happen. Preparedness, rather than prediction, remains the cornerstone of earthquake risk reduction. Among these active plate boundaries, the Manila Trench occupies a particularly significant position because it lies immediately west of Luzon, home to tens of millions of people. Along its northern reaches, the trench approaches the complex tectonic interaction near Taiwan. Farther south, it curves toward Mindoro, where plate geometry becomes increasingly complicated as additional tectonic blocks interact. This changing geometry has become a major subject of modern geological research. Marine seismic surveys have revealed thick sediment accumulations filling portions of the trench. These sediments do not simply rest quietly on the ocean floor. Under compression, they become folded, faulted, and incorporated into a growing accretionary wedge, where sediments scraped from the descending plate accumulate against the overriding plate. Within that wedge, buried thrust faults continue developing as convergence persists. Some of these faults may never produce significant earthquakes. Others could become important rupture surfaces capable of releasing substantial energy. Even more intriguing is the role played by underwater mountains carried toward the trench atop the descending plate. Known as seamounts, these massive volcanic features sometimes alter the mechanical behavior of the subduction interface. Rather than allowing smooth movement, they can distort surrounding rocks, create additional fractures, modify stress concentrations, and influence where future ruptures may begin or terminate. Marine geophysical studies have documented these complex interactions along portions of the Manila Trench, revealing that the boundary is far from uniform. Instead, it consists of numerous geological segments, each possessing distinct structural characteristics. Those differences may ultimately determine the size and extent of future earthquakes. Rather than behaving as one continuous fault stretching hundreds of miles, the trench may rupture in separate segments under certain conditions while combining multiple segments during rarer but much larger events. Determining exactly which portions remain strongly locked has therefore become one of the most important goals of contemporary research. That question has profound implications not only for earthquake magnitude, but also for tsunami generation, coastal hazard assessment, and emergency planning throughout the western Philippines and across the South China Sea. Meanwhile, the earthquake sequence west of Cataday continues, adding valuable observations to an expanding scientific record. Each seismic wave recorded by sensitive instruments travels through Earth's interior, carrying information about rock properties, fault orientation, rupture direction, and stress release. Individually, these earthquakes appear modest. Collectively, they provide another chapter in the ongoing effort to understand one of the most complex and potentially hazardous plate boundaries surrounding the Philippine archipelago. Long before modern seismographs began recording earthquakes with extraordinary precision, the Manila Trench had already been shaping the western edge of the Philippine archipelago through a geological process measured not in decades or centuries, but in millions of years. Every inch of convergence between the oceanic crust and the Philippine mobile belt has contributed to an immense storehouse of tectonic energy, much of which remains hidden from direct observation beneath several miles or several kilometers of seawater and thick layers of sediment. The absence of visible movement has never implied the absence of motion. In geology, silence often reflects accumulation rather than inactivity. One of the most important questions surrounding the Manila Trench is deceptively simple. Is the plate boundary continuously slipping, quietly releasing stress over time, or are significant portions locked together, allowing strain to accumulate until an enormous rupture finally occurs? Finding the answer has required decades of marine surveys, seismic imaging, satellite geodesy, numerical modeling, and careful examination of earthquake patterns. Unlike faults exposed on land, scientists cannot simply walk along the Manila Trench to measure fractures or offsets. Nearly the entire fault system lies hidden beneath the South China Sea, making every piece of information far more difficult to obtain. Researchers have instead relied upon indirect methods capable of revealing what cannot be seen directly. Among the most valuable tools are global navigation satellite system measurements. By monitoring the positions of highly accurate receivers distributed across Luzon over many years, scientists can detect ground movements measuring only fractions of an inch or only a few millimeters. Although these motions appear insignificant on a daily basis, they reveal whether the crust is slowly deforming as tectonic stress accumulates. Satellite observations have shown that western Luzon continues experiencing compression consistent with ongoing subduction along the Manila Trench. Rather than moving randomly, numerous locations exhibit gradual horizontal motion toward the trench, indicating that convergence between the tectonic plates remains active today. Those observations align with the long-term geological expectation that stress continues building within portions of the plate boundary. Peer-reviewed geodetic studies have concluded that several sections of the trench exhibit evidence of significant seismic coupling, meaning the two plates remain at least partially locked instead of sliding freely past one another. Such locking represents one of the fundamental ingredients required for future megathrust earthquakes. A completely creeping fault steadily releases accumulated strain through continuous motion, reducing the likelihood of extremely large earthquakes within that particular segment. A strongly locked fault behaves very differently. Friction prevents movement, even as tectonic forces continue pushing the plates together year after year. The longer this condition persists, the greater the amount of elastic energy stored within the surrounding rocks. Eventually, the rocks can no longer withstand the stress. When failure finally occurs, centuries of accumulated motion may be released within only a matter of minutes. That process has repeated itself throughout Earth's history across subduction zones worldwide. The devastating earthquake off Sumatra during the year 2004 ruptured an enormous section of the Sunda megathrust extending for hundreds of miles. 7 years later, northeastern Japan experienced another megathrust earthquake when the Pacific plate suddenly slipped beneath Honshu after remaining locked for generations. Those catastrophes transformed scientific thinking about subduction zones. Before those earthquakes occurred, many researchers believed certain faults might be incapable of producing ruptures as extensive as those eventually observed. Reality proved otherwise. Nature demonstrated that neighboring fault segments sometimes rupture together instead of independently, dramatically increasing the total magnitude released during a single event. That lesson has become particularly important when evaluating the Manila Trench. Rather than functioning as one perfectly uniform fault extending from Taiwan toward Mindoro, geological evidence indicates that the trench consists of multiple structural segments possessing different physical characteristics. Changes in sediment thickness, variations in plate geometry, differences in rock composition, and the presence of large underwater volcanic mountains all influence how stress accumulates and how future ruptures might propagate. Marine seismic reflection profiles have revealed remarkable complexity within the subduction interface. Some portions contain thick sediment packages scraped from the descending oceanic plate, forming a broad accretionary prism that continues growing as convergence proceeds. Other sections display rougher seafloor topography where ancient volcanic seamounts approach the trench. These underwater mountains may play surprisingly important roles. As a seamount enters the subduction zone, it does not disappear quietly into Earth's interior. Its massive bulk can deform surrounding rocks, alter local stress fields, fracture the overriding plate, and influence the strength of the plate interface itself. Some researchers have proposed that such features may act as barriers, limiting rupture propagation, while others suggest they may concentrate stress capable of initiating future earthquakes. The scientific community continues examining both possibilities because observations from different subduction zones have produced evidence supporting each mechanism under different geological conditions. Another important clue comes from the distribution of earthquakes themselves. When scientists map thousands of earthquakes occurring over many decades, distinct patterns begin emerging. Certain portions of the Manila Trench generate frequent moderate earthquakes. Other stretches appear comparatively quiet. At first glance, quiet regions might seem reassuring. Ironically, they sometimes produce the opposite interpretation. Within earthquake science, areas exhibiting remarkably little seismic activity, despite active plate convergence, are sometimes called seismic gaps. The concept does not guarantee that a major earthquake will occur there, but it raises important questions. If tectonic plates continue converging while relatively few earthquakes occur, where is the accumulated strain going? One possible explanation is that the fault releases stress gradually through slow creep. Another possibility is far more concerning. The fault may remain locked, storing energy that has not yet been released. Identifying which explanation applies requires integrating earthquake catalogs with geodetic measurements, marine geophysics, and numerical simulations rather than relying upon earthquake frequency alone. Several peer-reviewed investigations examining seismicity along the northern Manila Trench have identified patterns suggesting variations in locking behavior from one segment to another. Rather than behaving uniformly along its entire length, the trench appears divided into sections, exhibiting different mechanical properties and earthquake histories. That segmentation significantly complicates hazard assessment because neighboring segments could rupture separately during moderate events or combine during much larger earthquakes under the appropriate conditions. The possibility of multi-segment rupture explains why estimates of the trench's maximum earthquake potential have evolved over time. Earlier hazard assessments often considered individual fault segments independently. More recent numerical models have explored scenarios involving simultaneous rupture across multiple adjoining sections. Those simulations produce substantially larger earthquakes. The Philippine Institute of Volcanology and Seismology has repeatedly stated that the Manila Trench is capable of generating a maximum credible earthquake approaching magnitude 8.4. That estimate reflects present understanding of the trench's geometry, accumulated strain, and rupture potential, rather than any prediction regarding timing. Other published scientific models examining different assumptions about rupture length and fault dimensions have suggested that under certain geological circumstances, earthquakes exceeding magnitude 8.5 may also be physically possible, although the exact upper limit remains an active area of research. Magnitude alone, however, tells only part of the story. Equally important is the manner in which the seafloor moves during rupture. Megathrust earthquakes generate tsunamis because vertical displacement of the seabed forces enormous volumes of seawater upward or downward. Even a few yards or a few meters of uplift extending across hundreds of square miles or hundreds of square kilometers can initiate waves carrying tremendous energy across entire ocean basins. The Manila Trench occupies a particularly concerning position because it faces the enclosed waters of the South China Sea. Unlike the open Pacific Ocean, wave energy generated here interacts with coastlines belonging to multiple nations. Numerical tsunami simulations performed by researchers have demonstrated that western Luzon could experience the earliest arrivals within a relatively short period after a major rupture, while coastlines bordering China, Vietnam, Taiwan, Hong Kong, and other regions surrounding the South China Sea could also experience hazardous waves depending upon the rupture location and direction of energy release. These studies have made the Manila Trench one of the most extensively modeled tsunami sources in Southeast Asia. Another aspect attracting increasing scientific attention involves earthquakes occurring seaward of the trench rather than directly upon the megathrust itself. Known as outer rise earthquakes, these events develop within the bending oceanic plate before it descends into the mantle. As the plate flexes downward approaching the trench, extensional stresses produce normal faults capable of generating significant earthquakes. Although separate from the megathrust, outer rise earthquakes provide valuable information regarding stresses acting upon the descending slab. Researchers continue studying whether changes in outer rise seismicity sometimes accompany evolving conditions within nearby subduction zones. The relationship remains an active area of scientific research, with evidence varying among different plate boundaries around the world. No established method currently allows scientists to use outer rise earthquakes to predict imminent megathrust events, but these earthquakes contribute another important piece of the tectonic puzzle.